Hello friends, this is Gangadhar. This is another question from Advanced 2018, Paper 1 as an application of differentiation. See the question, for every twice differentiable function, f is from r to minus 2 to 2. So with f of 0 square plus f dash 0 square is equals to 85. So there are two conditions on function f. First one is f is a function from real numbers to minus 2 to 2. That in the sense, all the results, all the values of f of x are in the range of minus 2 to 2. Then directly it suggests us that minus 2 less than or equals to f of x less than or equals to 2. And which is nothing but mod f of x is less than or equals to 2. This is a direct condition given in the problem. And we have another one that f of 0 plus f dash 0 square is equals to 85. So we need to decide which of the following are the true statements. So we need to check each option one by one and to decide whether it is true or false using these two. And along with these two, one more condition on f is given that f is twice differentiable function. Since it is twice differentiable function, first derivative is not 0. Since first derivative is not 0, clearly f of x is not equals to a constant function. Since f of x is not a constant function, then the graph of f of x is not a line parallel to that. Since f of x is not a constant function, then the graph will be like this somewhere. Since the graph is like this, surely we may get two values, some r and s, such that in the interval rs, the function is 1, 1. For every value in between r and s, there exists unique f of x. Okay, and for every value for f of r to f of s, there exists unique value in between in the interval rs. So, since f of x is not a constant function, the graph of f of x will be like this. So surely there exists some small region rs such that f is 1, 1 in that particular region. So statement 1 is clearly a true statement. Then coming to the option B, second statement. We need to check whether it is true or false. To decide for the statement, I am going to apply Lagrange's mean value theorem for the interval minus 4 to 0. So if there exists some x naught as mentioned in the interval minus 4 to 0, then by Lagrange's theorem, f dash of x naught is equals to f of 0 minus f of minus 4 divided by 0 minus minus 4. Then this is nothing but what? F of 0 minus f of minus 4 by 4. See, the values of f of 0 are in between minus 2 and 2. For every x, f of x is in between minus 2 and 2. So clearly f of 0 is also in between minus 2 and 2. So minus 2 less than or equals to f of 0 less than or equals to 2. And f of minus 4 is also in between minus 2 and 2. Minus 2 less than or equals to f of minus 4 is less than or equals to 2. If you multiply this everything with minus, again you will get that minus 2 less than or equals to minus f of minus 4 is less than or equals to 2. If you add these two, you may get that f of 0 minus f of minus 4 is in between minus 4 to 4. Okay, so that means if you add these two, you have that minus 4 less than or equals to f of 0 minus f of minus 4 is less than or equals to 4. We need to divide the whole thing with 4. Then minus 1 less than or equals to this value divided by 4 less than or equals to 1. What is it actually by Lagrange's mean value theorem? This is f dash of x naught. So f dash of x naught values are in between minus 1 and 1. So surely mod f dash of x naught is less than or equals to 1. So by Lagrange's mean value theorem, for a point x naught in between minus 4 to 0, since they mentioned that f of x is in between minus 2 and 2, mod f dash of x naught is less than or equals to 1. So second statement is also a true statement. Then we need to check whether the third statement given is true or false. To check that one, what is given? Limit x tends to infinity f of x is equals to 1. Whether it is true or false, we need to check. To check whether limit x tends to infinity f of x is equals to 1, either it is true or false, we need to assume a function f of x such that whose range is in between minus 2 and 2, as well as it has to satisfy this condition. See, if you observe this one, f of 0 square plus f dash of 0 square is equals to 85. It is directly suggesting us that it is of the format something square plus its derivative square is equals to some 85. See, we know that sin square theta plus cos square theta is 1. So, if f of 0 or f of x is in the format of sine, then its derivative is of the format cos, and if you add directly you will get this as some 85. So, to make it as 85, I am taking f of x as some sine root 85x. If f of x is sine root 85x, then directly f dash of x is root 85 into derivative of sine is cos root 85x. So this is f of x and f dash of x is this one. If you take f of 0, then what is f of 0? F of 0 is 0, and if you take f dash of 0, since cos 0 is 1, this is root 85. Now f dash of f of 0 square plus f dash 0 square is clearly 85. So this sine root 85x is satisfying this condition. And its range is there, clearly in the range of this minus 2 to 2, and it is a twice differentiable function also. So the three conditions on f are satisfied by this function. So this is one of the function with those constraints. So I am going to check limit x tends to infinity for this f of x. See, as limit x tends to infinity, sine root 85x value is in between minus 1 and 1, but we don't know whether it is directly 1 or not. So this is a false statement. That we can't say it has directly 1. Okay? So it's a false statement. Then to check the fourth option, B. See, if you see here, there exists some alpha in the range of minus 4 to 4 such that f of alpha plus f double dash of alpha is equals to 0. For that, initially what we have to do? See, we need to assume a function g of x, some g of x, which is nothing but f of x plus f dash of x. Okay? Now, see, to check whether it is true or false, what I am going to do is, see, clearly we have that mod f of x is less than or equals to 2. Since mod f of x is less than or equals to 2, f square of x is less than or equals to 4. F square of x is less than or equals to 4. And we proved that the second option by Lagrange's mean value theorem, for a point in minus 4 to 0, f dash of x naught is less than or equals to 1 also. This, since f of, from this f square of x is less than or equals to 4, this is true for all the cases. Okay? See, what I am going to do is, just to change this one, take g of x as f square of x and f dash x square. Okay? Now, see, for some x1 belongs to minus 4 to 0. x1 is a point in the range of minus 4 to 0. For every x, f square x is less than or equals to 4. For a point in the range of minus 4 to 0, f dash of x naught is less than or equals to 1. By combining these two, for a point x1 in the range of minus 4 to 0, f square of x1 is less than or equals to 4, and f dash of x1 square is less than or equals to 1 from this. If you add these two, then it becomes g square of x1, which is less than or equals to, not g square of x1, just g of x1 is less than or equals to 5. See, for a point x1 in the range of minus 4 to 0, g of x1 is less than or equals to 5. Similarly, if you try for a point x2 in the range of 0 to 4, again you will get that g of x2 is also less than or equals to 5. So, if I consider a function g of x with this definition, then clearly there exist 2 points x1 x2 such that x1 is in the range of minus 4 to 0 such that g of x1 less than or equals to 5, and x2 is in the range of 0 to 4 such that g of x2 is less than or equals to 5. Also with these conditions we have that g of 0, the value of g of 0 is f square of 0 and f dash 0 square, which is nothing but 85. So, okay, so now I am going to imagine the graph of g of x with these three. Since g of x1 is less than or equals to 5, g of x2 is less than or equals to 5, g of 0 is 85, and x1, x2 are like this. With these three, if we try to imagine the graph of g of x, then the graph will be like this. How the graph? See, usual x-axis and usual y-axis, and at 0, g of 0 is somewhere 85. And if you took something, this is 5, so minus 4, and this is 4. So in between 0 to minus 4 to 0, we have somewhere x1, and the range of 0 to 4, we have somewhere x2. So maybe x1 may be anywhere. See, for x1, for any x1 in this region, the value of g of x1 is less than or equals to 5. So below this 5, so somewhere just took it as something here. And again x2 is in the range of 0 to 4 and its value is less than 5, somewhere took it as like this. Okay. So the graph passes through these 3 points. Since the graph is passing through these 3 points, surely it may take a maximum value somewhere in between minus 4 to 4, somewhere in between x1 and x2. See, surely it has a point, some alpha, where it may get a maximum value. So if it get a maximum value there, then its derivative at alpha is 0, so g dash of alpha is equals to 0. Since g dash of alpha is 0, then the derivative of this one is 0. So the derivative of this one is 0 at alpha, then we will write it like this. See, its derivative is 2 f of alpha into f dash of alpha. Derivative at alpha I am taking, plus, and for this 2 f dash of alpha into f double dash of alpha is equals to 0. And if you come out that 2 f dash of alpha, we have that f of alpha plus f double dash of alpha is equals to 0. As they mentioned that f dash of alpha not equals to 0 in the option itself, this is not equals to 0, so clearly this is 0. So we have an alpha in the range of minus 4 to 4 such that this is 0. So this option D is somewhat difficult to verify, but this is also a true statement. So for this problem, if you observe, option A, B and D are true and option C is a false statement. So this is one of the tricky problem on the application of derivatives asked in advanced 18 paper 1. Thank you.